Okay. So in the last class, we started on design of gravity dams, and we looked at how to calculate the different forces acting on dams. So we started with water pressure, and then uplift, pressure due to earthquake, hydrodynamic forces due to earthquake, silt pressure, wave pressure, wind, and ice. So we looked at calculation of all these different types of forces, and then what we did was to look at the combinations of loads for different conditions as prescribed by the IS standard, which is 6512 1984. So I'm not going to go in details about the calculations again. I'm just going to show you briefly so you remember what we did last time. So these are the different forces acting on the dam, starting with, let's say your free surface is here, then you would have hydrostatic pressure. And similarly on the downstream, you have free surface here, so you have hydrostatic pressure because of the tailwater. And the self weight of the dam is what is resisting these forces, along with any vertical forces that are acting. So in this case, there is a vertical hydrostatic force that is acting on the upstream face, which is at an angle with the vertical. So it is not totally vertical. It has some angle, so that there is a weight on top of this, and that is also going to resist the forces that are trying to push the dam in this direction. And the hydrodynamic pressure mainly comes when you have an earthquake. There is a lot of acceleration of the still water body. Because of this acceleration or sudden motion of the body, the water body is going to exert inertial forces, and that is not linear with depth. It is a non-linear function with depth. So that is why you have non-linear increase in the hydrodynamic pressure. And you have uplift pressure, which is dependent on the tailwater level and the upstream water level. And if you have any galleries or drainages that releases the water, so water has tendency to percolate into the dam through the pores, and also it can seep into the foundation. So it is going to exert uplift pressure. And if you have galleries, then whatever the water is percolating and seeping through, you're removing it so that you're releasing some pressure. So that reduces the uplift force on the base of the dam. Now, if there are no drains, then the uplift pressure is going to be higher. And if you have drains, then you're relieving some of the uplift pressure. So what we also did last class was to start with the problem on the design of the dam. And we were given some data in the question on the dam conditions. And based on those conditions, we tried to first estimate the top width based on if you want to have a road for access on top of the dam, then the width is dependent on the width of the road that you want to provide. And what we also did was to calculate the freeboard on top of the full reservoir level. So this freeboard is required so that there is no overflow of water on top of the dam. And this freeboard is dependent on several factors, like if you have wind, that is going to cause waves, wind waves, and the wind waves are going to get slosh on the upstream face of the dam. And you don't want this sloshing to overtop the dam. So your freeboard should be sufficient to not let the water overtop the dam. So based on the dimensions of the dam, that is the free Sorry, there was power outage. Let me share my screen again. Can you see my screen?
Yes, sir.
Okay. So last time we did this problem, we started and calculated the forces on the dam. Now today what we are going to see is the modes of failure of gravity dams and what are the factors that we need to consider when estimating the stability of the dam. So in today's class, I'm not going to show you any numbers. So I will upload a tutorial sheet along with some example problems with solutions so that you can solve yourself or you can try along with the solutions. But today I'm going to talk you through conceptual things of stability of gravity dams. So there are different modes of failure for gravity dams. So one is by overturning. So in the last time, what we did was calculate all the forces, vertical and horizontal, that are acting on the dam section. And once you calculate all the forces, then what you can do is to get the moments of each of these individual forces. So let's say you have hydrostatic force on both sides, and then you have the self-weight, hydrodynamic pressure, and self-pressure, wave pressure. So all these forces, you have the magnitude of the forces, and you also know the points where these forces are acting on the section. Now, with respect to the toe of the dam, we take the moments of each of these forces, and whatever the force is acting in clockwise direction is considered as a righting moment, or it is considered as overturning moment, which is trying to push the dam in the downstream direction, which is going to lead to instability of the dam. So what we want is this dam to be stable, and the forces acting in the clockwise direction should be counteracted by forces acting in the other direction. So you have overturning moments, and those are to be balanced by the righting moments, which are trying to give stability to the dam. So if clockwise are negative moment, then we need to have anti-clockwise moments that are trying to stabilize the dam. And if you take the ratio of the righting moments to the overturning moments, you get a factor of safety. So this is a factor of safety against overturning, and that factor of safety should be usually more than 2 for normal loading when you do not consider, for example, earthquake conditions. When you consider earthquake conditions or extreme loading, when you don't have any drains operated, when you have the uplift as the maximum, then the factor of safety should be at least 1.25. So this is the ratio of the righting moments which provide stability to the dam in anti-clockwise direction to the moments that are trying to destabilize the dam. Now I'm not showing you any numbers, but I will upload an example by Friday so that you can go through the numbers as well. The second condition is sliding. So the first is overturning, and the second is sliding. So the dam should be stable without any horizontal motion. Now the factor of safety against sliding is calculated by this ratio. So you have the sum of forces which are trying to move the dam in the horizontal direction, and these horizontal forces are counteracted by the frictional resistance at the base. And this frictional resistance comes from the vertical forces that are acting and multiplied by a friction coefficient mu. So all the horizontal forces that are trying to, or the resultant horizontal force that is trying to move the dam in the horizontal direction is counteracted by this frictional force. And this factor of safety should be at least 2 for normal conditions, and it has to be at least 1.2 for extreme loading again. Now this is for small dams. Now if you consider any higher dams or when the height of the dam is more than 100 meters, then usually the dam is built in stages. So let us say this is the section of your dam, and usually you start putting concrete up to this level, and then you would put concrete on top of that level. Again, you would put concrete on top of it. So you're going to use, or you're going to build the dam in stages. So when you are building the dam in stages, you would be providing joints between the two sections of concrete. So this is a joint here. And here, this is a joint again. So you have different joints that are along the section of the dam. And these joints are also going to provide some frictional resistance or the shear resistance against the horizontal forces. So for very high dams, you can consider those frictional or shear strength because of the joints as well. C is the shear strength of the joint material multiplied by the shears by the cross-sectional area on which this shear strength is acting. So here, because we are considering per unit length of the dam, the area is B times 1. So simply it becomes B, that is multiplied by the shear strength of the joint. So you have the usual vertical forces multiplied by the frictional coefficient. And in addition to this, you have another force, which is because of the shear strength of the joint. Now this factor of safety against sliding should be more than 2 for normal conditions. And the cohesion or the shear strength of the joints is usually considered as 1300 kilonewtons per meter square if you are using concrete. Also, there is a sliding factor, which is tan theta, which is simply the ratio of horizontal forces to the vertical forces. So for different loading conditions, the factor of safety against sliding is different. So for example, loading conditions A, B, and C, the factor of safety should be 2. For loading conditions D and E, it should be 1.5. For F and G, it has to be 1.2. So different operating conditions of the dam have different safety depending on the loading. So far we have seen overtopping and sliding, and the next one is compression or tension. So in this case, we are going to consider the stress on the base of the dam. So let's say this is the base of the dam. So you have, this is extending, this is the downstream face of the dam. And this is extending, this is upstream face of the dam. Right. So we are looking at the base of the dam, and we want to calculate what are the stresses acting on the base of the dam. So let's say H is the resultant horizontal force and V is the resultant vertical force, and R is the resultant of both horizontal and vertical forces. Now the line of action of R at the base is, let us say, acting at a distance E from the center of the dam or center of the base. So at this point, from this point, the heel is at a distance of B/2 and the toe is also at a distance of B/2. But the resultant force is acting at a distance E. So E is the eccentricity of the force. Now, because of this resultant force, you are going to have, or because of the eccentricity, you are going to have bending stress as well. So directly because of the vertical force, you have normal stress on the base, which is simply the force divided by the area. And because of the resultant force acting at an eccentricity, you would have bending stress. That is because of this R. Now you can calculate this bending stress, and you can get this value as 6VE by B squared. So where you have M is the force, Y is the eccentricity, and I is the in moment of inertia. So you get the bending stress as well, which is plus or minus 6VE by B squared. Now the total normal stress on the base is sum of both the normal stress and the bending stress, which is V by B plus or minus 6V by B square. And you can represent this, if you take out the V by B factor, then it becomes V by B 1 plus or minus 6E by B. Now this eccentricity E is important. Depending on this eccentricity of the load, the stresses at the base of the dam are going to change. Now, in the first case, let us say the eccentricity E is less than B by 6. So this is the center of the dam, and your eccentricity E is less than B by 6. And if you substitute E less than B by 6 in this equation, then both the sides would both 1 plus 6E by B or 1 minus 6E by B would be positive. So you would have compression here, which is because of V by B multiplied by 1 plus 6E by B. And here you have a smaller compression stress, which is V by B 1 minus 6E by B. So this is when the eccentricity is less than B by 6. Then you have both at heel and toe, you have compression stresses. If the eccentricity is exactly B by 6, then if you substitute E equals to B by 6, then on one side it becomes 0. On the other side, you would have V by B, so 1 plus. So this would be 2V by B. So there is no compression or tension at the heel, but there is compression at the toe. Now in the third condition, when you have E more than B by 6, then you would have compression here and tension at the heel. So I'm just using this equation here, which is the total normal stress at toe by using 1 plus 6E by B, and at heel 1 minus 6E by B, and I'm just changing E from E less than B by 6, E equals to B by 6, and E more than B by 6, and I'm calculating what is Pn at the toe and what is Pn at the heel. So this is what you get for the 3 different conditions. And under no conditions, you should allow tension at the base of the dam. So if your forces and the moments are such that you are getting tension at the heel of the dam, then you need to redesign the dam so that there is no tension at the base of the dam. So whereas compression, there should also be a limit for compression. So you cannot allow the stress to be higher than what the material can take. So for example, for concrete, there would be an allowable compression stress of concrete. So the stress at the base of the dam cannot exceed the stress of the concrete, allowable stress in concrete. So this total normal stress should always be less than which is allowable in the foundation. So by considering the 3 different conditions, when you have E less than B by 6, E equals to B by 6, and E more than B by 6. So if E is more than B by 6, then you have tension, so which is not permissible. And if E is less than B by 6 or E is exactly B by 6, in both the cases you have compression. So which means compression is acceptable given that it is within the limits of the foundation material. Now if I'm considering the resultant force R with an eccentricity from the center line of the base, so I'm saying this is B by 6, and it could be on the other side as well, so it could be B by 6 towards the heel. So if you sum up B by 6 plus B by 6, which is the range within which the resultant can fall in, then that becomes B by 3. So your resultant force should always lie within the second 1/3 of the dam base. So if you divide the base into three parts, b by 3, b by 3, and b by 3, the resultant should always lie within the second 1/3 of the dam. So it should not be either in this section or it should not be in this section. So it has to be in the middle 1/3 of the dam. And then what we are going to look at is the principal stresses and the shear stress in the dam. So Pn is the total normal stress. I'm just notating the same normal stress as sigma y, which is V by B, 1 plus or minus 6C by B. So this we have derived earlier. Now, if this total normal stress is at the toe, then I am representing as sigma y d. If it is at the heel of the dam, then I am representing that as sigma y u. So the same normal stress, I'm just changing the notation so that we have different conventions for toe and heel. So if it is at the toe, then it is sigma yd. If it is at the heel, then it is sigma yu. And we are going to consider principal planes here. So a principal plane is when there are no shear stresses on the plane. So earlier I said that when we construct the dam, you would be constructing in different stages. So first you would be constructing from the base up to this section of the dam, and on top of this, you would be again laying concrete for the second section, and on top of that, you would lay concrete again. So you are building dam in different stages. And let us say we consider hydrostatic force, which is horizontal. Now this horizontal force, if you look at the upstream face of the dam, is acting at 90 degrees, or it is normal to the vertical, or sorry, it is normal to the upstream face. So the hydrostatic force is normal to upstream face. And then because of the horizontal forces, you also have shear stresses and the shear force developing at the joints. So you have shear stress or shear force at the joints. So the section of the dam where the face of the upstream is vertical, this cannot be principal plane because there are shear stresses along these sections. Whereas here, let us say you are providing the upstream face at an angle to provide additional forces to the dam, then on this upstream face, the hydrostatic force is going to act normal, but there is no shear force if you consider here in this direction, normal to the hydrostatic force. So your shear is going to be like this, but the shear is not in the direction of the hydrostatic force. So this plane can be considered a principal plane. Similarly, on the downstream, this is the hydrostatic force. Then there is no shear force along the hydrostatic force. So that is why even this downstream face can be considered a principal plane. Now I'm going to take a triangular element on the downstream face or at the toe. This triangular element is ABC, and I'm calling this AB as my principal plane because there is no shear stress in the direction of the hydrostatic pressure. I am showing that ABC here again. So this is the hydrostatic pressure acting on the face AB. Now there is a plane which is normal to the to this plane AB at an angle 90 degrees. BC is also a principal plane. So you have principal planes that are AB, BC. And the corresponding normal stresses acting on AB and BC are P dash and sigma 1D. And you have the base of the dam, which is AC. AC also has a normal stress, which is sigma YD. So sigma YD is the total normal stress we calculated earlier. But at the base AC, you also have shear stress, which is acting in this direction, in the horizontal, which is because of the friction. So you have three planes AB, BC, and CA, and the corresponding normal stress and the shear stress are P prime, sigma 1D, and sigma YD, and tau YX. So these are the normal stresses and the shear stresses acting on this triangular element. Now, if the dam is stable, then there is no motion in the dam and there is also no tilting in the dam because the dam is stable. Now, for the dam to be stable, there has to be equilibrium of forces. So what we do is to consider all the forces in the vertical and consider all the forces in the horizontal, and we try to equate them and get equilibrium. So once you do equilibrium, then you can calculate the stresses or the principal stresses that are acting in the dam. So looking back at this picture, you have sigma 1D, P prime, and sigma YD. And what we want to do is to equate these forces in the vertical. So we have to resolve these forces in the vertical direction first, and then try to equate them. And the angles I have shown here of the triangle. So based on these angles, we try to resolve these forces in the vertical direction and then equate them. So sigma 1D is the stress, and this stress is acting on the area dr times 1. So we are considering per unit length of the dam, and I'm saying here the length of these triangular sides. AB has a length of ds, a small elemental length. BC has a length of dr, and CA has a length of dx. And using the angles of the triangle and the lengths of the sides of the triangle, we can resolve the forces in the vertical direction. So you have sigma 1D with dr times 1, which is the area stress. So this is stress multiplied by the area, you get the force, and you resolve that in the vertical direction with cos phi d. And P is again the hydrostatic pressure. So you need to multiply pressure with area. So you get area, and you resolve that in the vertical direction using sine phi d, which is the angle. And that is, and these two forces are counteracted by sigma by d, which is the stress multiplied by area again. So sigma by d is already in the vertical direction, so you don't have to resolve it or multiply it with cos or sine phi d. Now within this right angle triangle, you can also get the relation of cos phi and sine phi. So cos phi is dr by dx and sine phi is ds by dx. So if you substitute this here, then you can simplify the equation to get what is sigma 1d. So sigma 1d would be sigma yd secant square phi d minus p1 tan square phi d. So this is the principal stress acting at the toe. Now, if you consider the tailwater is very low, or there is no tailwater, Then the hydrostatic pressure, you can consider that as 0. Then your principal stress is simply a function of total normal stress multiplied by a factor secant square phi d. So through this relation, what you get is the principal stress that is acting on this plane is always higher than the compression or tension at this location. So the principal stresses are higher than the compression stresses at the toe. So when you want to select a material for constructing the dam, you should check for the principal stresses if this sigma 1d is less than or equal to the allowable stress of the material. So you should make sure that your material, let's say concrete, is able to withstand the stress sigma 1d. So if not, then you need to revise the design or revise the material choice. So what we did was to resolve the forces in the vertical direction. Now what we try to do is to resolve the forces in the horizontal direction. So again, I'm showing you the same triangle. So here you have a shear stress at the base, which is tau yx, and sigma 1d and p prime are acting at an angle on these planes, which can be resolved into horizontal directions. So if you try to resolve these p prime and sigma 1d in horizontal direction and equate to the shear stress, this is what you get. So the shear stress is acting on an area of dx by 1. And you have sigma 1d, which is the principal plane stress or the principal stress acting on an area dr times 1. And then you have hydrostatic pressure acting on an area ds1. So if you simplify this, you can calculate what is this shear stress. Now, if you substitute for sigma 1d from earlier calculation, earlier we have calculated sigma 1d. So if you substitute that and simplify, you would get tau yx as sigma yd minus p prime multiplied by tan phi d. And again, when you consider that the tailwater is very low or there is no tailwater, then you can neglect p prime here. So what you get is tau yx is sigma yd tan phi. So this is again, you need to make sure that the stress is acceptable depending on the choice of material. So these are the different stresses that you need to consider when checking for the failure of dam. So just to revise the concept of failure of dams, what we did was first to check for overturning by considering the different forces and the resulting moments on the dam. And the second is to consider failure because of sliding. So you have horizontal forces that are trying to destabilize the dam, and that is contracted by the friction, which comes from the self weight and the frictional coefficient. And the third is we checked for compression or tension in the dam at the toe or heel. And then we also did principal stress. So you need to consider all these 4 factors when checking for safety of the dam. Now let's talk about galleries. So I briefly mentioned about galleries when we started design of the dam. So you provide galleries inside the dam section so that whatever the water is seeping either through the foundation or through the upstream phase can be released and drained through the drainages. So once you provide this gallery for drainage, then you're actively relieving uplift pressure. So you're reducing the vertical forces that act on the foundation of the dam. Now, there are multiple purposes for providing this drainage. The primary purpose is to provide seepage, to provide drainage for the water that is seeping through foundation. But once you provide this gallery, you can also use it as a walkway where people can walk through and do maintenance of the dam. For example, if you want to inspect the inspect the strength of the dam. So let's say the dam has been constructed 20 years ago and you want to see the strength of the dam, probably you can use this walkway as an access to the inside of the dam and you can assess the strength of the dam. Or you can provide piping and also provide electrical equipment or lighting inside the gallery so that active maintenance can be taken. So you can also do inspections or provide visitors and inside access of how the dam is. And also you can use this gallery for operating mechanical equipment or for moving for equipment that needs to be transported, let's say for testing the strength of the material of the dam. So this has multiple purposes, so not just drainage. And this width of the gallery depends on how much you want to provide for walkway. And once you provide this gallery, the uplift pressure is going to be relieved. So this is about galleries. And then we are going to talk about elementary profile of a dam. So let me show you something else briefly. So this is the profile or section of a dam that I showed you when describing the forces acting on the dam. What you see here is there is a top width. For example, if you want to provide a road for transporting from one side of the dam to the other side, then the top width is dependent on the width of the lane. You also have a freeboard here to consider for the waves that are generated because of the wind and overtopping. And you have an upstream slope to provide resistance. So if you, for example, if you just consider an vertical face of the upstream, then it may not be sufficient to withstand the forces. By providing an inclined face on the upstream, you have water that is acting downwards, and that is going to provide you stabilizing moments. So the overturning moments are in the clockwise direction, and the stabilizing moments are in anti-clockwise. So this vertical portion of the water in the reservoir is going to provide you a moment in the anti-clockwise direction, which is going to resist overturning. So that is why we provide an inclined surface or inclined face on the upstream. So this is called a practical profile. So in this practical profile, we consider a top width and we also have an inclined upstream face. Whereas if you consider an elementary profile, this is purely a theoretical profile. So let us say we are not considering earthquake forces, or we are not worried about access on top of the dam. So we are just simply considering three forces, that is hydrostatic pressure, uplift, and self-weight. Then this theoretical profile would be a right-angled triangle. So only for considering the three forces, self-weight, uplift, and pressure, a simple right-angled section or a right-angled profile is sufficient to withstand the forces. So this is called elementary profile. So this is a very simplified case and a theoretical profile. Here we are not considering any tailwater, so there is no tailwater. So you simply have upstream hydrostatic force, uplift force. Because there is no tailwater, the uplift force here is zero. You have some uplift pressure on the upstream, and you have the self weight of the dam. Now, again, if you consider the stability of the dam, the resultant moment should be 0. So whatever, because of the three forces, you calculate the moments because of each individual force, and the moments that are acting in the clockwise should be balanced by the moments that are acting in the anti-clockwise direction. So for stability, the sum of the moments should be 0. So in this case, the moments that are acting or that are trying to destabilize the dam are the hydrostatic pressure and the hydrostatic force. So the hydrostatic pressure is P and it is acting, sorry, this is the hydrostatic force acting at a height of h by 3 from the base, because this is a triangular section. It acts at the centroid, which is h by 3. And the uplift pressure is also acting at the centroid, which is b by 3 from the upstream phase. And these two moments are counteracted by the self weight, which is acting at the centroid again, which is b by 3. So we are equating the destabilizing moments to the stabilizing moments. And if you substitute for the hydrostatic force, the uplift force, and the self weight of the dam, you simplify this equation and you get an expression for the bottom width of the dam. So you have the bottom width, which is a function of the height of the dam divided by square root of s minus 1. So s is the specific gravity of concrete. So usually it is 2.4. So your base width you can calculate if you know the upstream water level, and if you know the type of material, for example concrete, then you can calculate the base width. So now you have the dam dimensions. So let us say if we neglect the uplift pressure, then it simply becomes h by square root of s. So this is the bottom width. Now, if you consider no sliding condition, so first is overturning or overtopping, you could say. And the second condition is sliding. Now again, for sliding, the horizontal force is balanced by the frictional force at the base. So this is the horizontal force, which is the hydrostatic force that is trying to push or move the dam, and that is contracted by the resultant vertical force multiplied by the frictional coefficient mu. And B, if you simplify this equation, it's simply h divided by mu times s minus 1. And again, if you consider there is no uplift pressure, then B is h by mu times s. So s is again specific gravity. So earlier we have calculated the base width based on overturning. Now we have calculated the base width based on sliding. So the final width of the dam should be higher than either because of overturning or sliding. So this is because of sliding, sorry. This is because of overturning, and this is because of sliding. So the dam width B should be more than both of these two calculated widths. And if there is no uplift, then the dam width should be more than these two calculated values. So this is calculated for overturning condition, and this is calculated for sliding condition. So the width of the dam should be higher than these two values when there is no uplift. When there is an uplift, it has to be higher than these two values. So now you have the width of the dam at the base, and it's simply a right angle triangle, and the height is dependent on the water level. And finally, what is the limiting height for the dam? For example, we have a material concrete, and that concrete has an allowable stress of certain value. And the height of the dam is also dependent on the allowable stress of the material of the construction. So if you consider the stress, which is sigma 1d, that would be gamma h multiplied by the specific gravity. And the height of the dam would be a function of sigma 1d by gamma s. And sigma 1d should be less than or equal to F, which is the allowable stress in the material. So your H is a function of allowable stress of the material divided by gamma S. When there is uplift, and when there is no uplift, then H is a function of F divided by gamma multiplied by S plus 1. So this is a simple derivation that you can do as well. So this is about the elementary profile. So an elementary profile is a pure theoretical profile. In practice, we are not going to provide a right angle section without any top width. So in practice, we are always going to provide some top width, and we are going to provide freeboard. And if required, we are also going to provide an inclined section on the upstream face of the dam. So whereas an elementary profile is simply a right angle triangle. So this is the design of dams, and related to this, I'm going to upload a solved example and also a couple of problems on designing or checking the design of dams. This would be available on Friday. I will upload on the Google Classroom, and you can try to solve it yourself. If not, you can discuss with me if you want any help again. In the next class, we are going to start earthen dams. And once we finish earthen dams, we also have to cover spillways, types of spillways. So that's all for today's class. Any questions on this so far? Can you hear me?
Yes, sir.
Yeah. So I'll upload the lecture notes and as well as the recording on Google Classroom as well. And the tutorial will be uploaded on Friday. And next week we will have two classes. One is the usual time on Monday, and Wednesday between 9 a.m. to 10 a.m. we will have one more class because we missed one of the classes in the first few weeks. So we need to cover that. So next Wednesday between 9 to 10 a.m. we will have an additional class. All right, so if there are no questions, then I'll close the session. I'll upload all the materials and I'll see you on next class on Monday.
Thank you, sir.
All right. Thank you. Bye.